Researchers are utilizing the new James Webb Space Telescope, JWST, to focus on Neptune's largest moon, Triton. Unlike older telescopes, JWST can see infrared light which is invisible to our eyes. This light can reveal the composition of Triton's surface, its atmosphere, and even hints of a hidden ocean. JWST may be able to take images of Triton's surface, but not in the way a rover would. Instead of traditional photos, it captures infrared data, creating detailed maps of the moon's structure and temperature. Triton's surface is primarily composed of frozen nitrogen, with traces of methane and carbon monoxide ice. These materials reflect sunlight, making Triton one of the most reflective bodies in the solar system. Although Triton has a thin atmosphere, it consists mainly of nitrogen with small amounts of methane. JWST's infrared instruments can analyze how sunlight interacts with this atmosphere, helping scientists understand seasonal changes and atmospheric escape processes. One of the biggest mysteries surrounding Triton is the possibility of a subsurface ocean. Neptune's gravitational pull could generate enough heat to keep liquid water beneath Triton's icy shell. While JWST cannot directly see this hidden ocean, it can look for signs, such as thermal anomalies on the surface. If unexpected heat signatures are detected, it could suggest water rising from below, possibly through cryovolcanism. Triton's potential for life is another intriguing question. If a subsurface ocean exists, it may contain the necessary conditions for microbial life, similar to Europa and Enceladus. Cryovolcanic activity could release organic molecules, which JWST could detect in Triton's thin atmosphere. These findings could help scientists understand whether icy moons can support life. JWST's advanced instruments allow scientists to study Triton in unprecedented detail. The near-infrared camera, NIRCam, can penetrate atmospheric haze and detect surface materials. The near-infrared spectrograph, NIRSpec, breaks down light into its component wavelengths, identifying molecules and measuring temperature variations. The mid-infrared instrument MIRI can detect faint thermal emissions, helping scientists identify geological activity and surface changes. Studying Triton could provide insights into the early solar system. Triton is believed to be a captured Kuiper Belt object, meaning its origins could be similar to Pluto's. Understanding its history could shed light on how Neptune and other outer planets influenced the migration of icy bodies. Exploring Triton is challenging due to its great distance from Earth, about 2.8 billion miles. Future missions would require innovative solutions, such as nuclear power for long-duration exploration. While JWST lays the groundwork, an orbiter or lander could provide direct measurements of Triton's surface and atmosphere. Careful planning would be needed to avoid contaminating Triton with Earth's microbes, ensuring any signs of life detected are truly extraterrestrial. The study of Triton also contributes to a broader understanding of icy moons throughout the solar system. By analyzing its composition, orbit, and potential for a subsurface ocean, scientists can refine theories about planetary formation and habitability. Triton's retrograde orbit suggests a dramatic past, likely involving a violent capture by Neptune's gravity. Investigating these dynamics helps researchers understand how giant planets interact with their moons. JWST's observations are only the beginning. The data gathered will inform future missions, potentially leading to a dedicated Triton orbiter. A combination of telescopic studies, flybys, and landers will help scientists piece together the full picture of this enigmatic moon. Triton, once a distant mystery, is slowly revealing its secrets, bringing us closer to understanding the outer solar system. Future studies of Triton could also influence how scientists approach exoplanet research. Many exoplanets orbiting distant stars are icy worlds, potentially similar to Triton. By understanding the processes at work on this Neptunian moon, researchers can refine their models for studying planets beyond our solar system. Observations of Triton's thin atmosphere, geological activity, and potential subsurface ocean could offer clues about habitability conditions on exoplanets with similar compositions. Additionally, Triton's unique characteristics, such as its retrograde orbit and active surface, make it an essential target for planetary science. Unlike most large moons which form around their host planet, Triton was likely a captured Kuiper Belt object. This past event may have drastically reshaped its interior and surface, leading to the geological activity seen today. If researchers can confirm past or present cryovolcanism, it would provide direct evidence of internal heating, an essential factor in determining whether a moon or planet can sustain liquid water. Advancements in space technology will play a critical role in furthering Triton exploration. Current mission proposals, such as NASA's Triton concept, suggest a flyby to study the moon's surface, atmosphere, and potential ocean. While JWST provides valuable remote observations, a spacecraft visiting Triton would allow for higher-resolution imaging and direct sampling of its thin atmosphere. Instruments capable of detecting organic molecules, measuring ionospheric activity, and mapping surface features in detail could revolutionize our understanding of this icy world. Long-term exploration of Triton could even include the possibility of a lander or probe that drills beneath the surface to search for signs of a subsurface ocean. If such an ocean exists, scientists would need to determine whether it remains liquid due to internal heating or external tidal forces from Neptune's gravity. Studying the thickness of Triton's ice shell and its thermal properties could provide crucial evidence. Beyond Triton, exploring other icy moons, such as Europa, Enceladus, and Ganymede, will help scientists compare their findings. Each of these moons exhibits unique characteristics, but all share common questions regarding subsurface oceans and habitability. By studying multiple examples, researchers can refine their understanding of which conditions are most likely to support life in the outer solar system. As technology continues to improve, future missions will likely provide even more detailed insights into Triton's mysteries. The combination of JWST's observations, upcoming spacecraft missions, and potential lander explorations could reveal whether this distant moon harbors the conditions necessary for life, or if it is a frozen relic of the solar system's past. Whatever the findings, Triton remains one of the most intriguing and enigmatic destinations for planetary exploration. The study of Triton is not just about understanding a single moon. It is about uncovering the broader history of our solar system and the potential for habitable environments beyond Earth. As scientists gather more data, they will be able to piece together the story of Triton's origin, its dynamic processes, and the forces that have shaped its surface over billions of years. One of the key mysteries that future missions could help unravel is whether Triton is still geologically active. While past observations suggest cryovolcanism and resurfacing events, JWST's infrared capabilities will allow scientists to detect temperature variations that could indicate ongoing activity. If Triton is still geologically alive, it could mean that internal heat sources, such as radioactive decay or tidal interactions with Neptune, continue to influence its evolution. This would be a groundbreaking discovery, as it would suggest that even distant icy moons can remain active over long periods. Another significant question is whether Triton's potential subsurface ocean has persisted over time or if it has frozen solid. If JWST or future missions detect signs of liquid water beneath the ice, it would drastically change our understanding of Triton's potential for life. Many of the icy moons suspected of having underground oceans, like Europa and Enceladus, are closer to their host planets and experience strong tidal forces that help maintain their liquid interiors. Triton, however, is farther from Neptune and experiences a more complex gravitational interaction. Determining whether it has retained liquid water would provide new insights into how subsurface oceans form and persist in different planetary environments. Triton's atmosphere, though thin, also holds valuable information about its past and present conditions. Seasonal changes on the moon could reveal how volatile compounds like nitrogen and methane cycle between the surface and atmosphere. By studying these processes, scientists can better understand how atmospheres evolve on icy worlds and what that might mean for planets and moons in other star systems. JWST's ability to analyze the chemical composition of Triton's atmosphere could also identify unexpected elements that hint at hidden geologic or atmospheric interactions. Looking beyond the JWST era, the future of Triton exploration may involve next-generation space telescopes, orbiters, or even landers equipped with instruments capable of detecting biological signatures. If Triton's surface features signs of organic molecules, as some scientists suspect, it would raise even more compelling questions about the potential for life in our solar system. A future lander or probe could directly sample surface materials, analyze their composition, and even drill into the ice to search for signs of habitability. Ultimately, Triton remains one of the most intriguing yet least explored worlds in our solar system. Each new observation adds another piece to the puzzle, bringing us closer to unlocking its secrets. As our technology and understanding advance, Triton may go from being a distant, enigmatic moon to one of the key locations in our search for life beyond Earth. Whether it holds an active ocean, hidden geological processes, or unexpected atmospheric chemistry, the discoveries awaiting us on Triton have the potential to reshape our knowledge of planetary science and astrobiology. The ongoing exploration of Triton is not just about this distant moon itself, but also about understanding the broader mechanisms that shape icy worlds throughout the solar system and beyond. If Triton indeed harbors a subsurface ocean, it could significantly expand the list of potentially habitable environments, adding to the growing evidence that liquid water can exist in surprising locations, even far from the Sun. A major focus of future studies will be the interaction between Triton and Neptune. As a captured Kuiper Belt object, Triton's presence has likely influenced Neptune's evolution, and vice versa. The gravitational forces at play between the two bodies may contribute to internal heating within Triton, affecting its potential subsurface ocean and surface activity. Detailed observations of Triton's orbit and rotation could provide clues about its internal structure, including whether an ocean still exists beneath its frozen exterior. Further, Triton's highly reflective surface suggests that it is continuously being resurfaced, possibly through cryovolcanic activity. If active plumes or geysers exist, future missions could sample these ejections to analyze their composition, much like the Cassini spacecraft did at Enceladus. This would offer a direct way to study the moon's internal chemistry without needing to drill through miles of ice. JWST might be able to detect signs of recent surface changes, but a dedicated orbiter or lander would be necessary for more precise measurements. The study of Triton also has implications for exoplanetary science. Many exoplanets and their moons exist in cold, distant regions of their star systems, similar to Triton's environment. By understanding how volatile compounds behave on Triton, scientists can refine models for exoplanet atmospheres and surfaces, helping us interpret data from telescopes studying distant worlds. As technology progresses, missions specifically designed to explore Triton could become feasible. A dedicated spacecraft could map its surface in high resolution, measure its atmospheric composition in detail, and even deploy landers or ice-penetrating probes to search for underground water. Given the vast distance and challenges of reaching Neptune, such a mission would require advanced propulsion systems, nuclear power sources, and innovative landing technologies. However, the scientific payoff would be immense, potentially providing answers to fundamental questions about planetary formation, ocean worlds, and even the possibility of life beyond Earth. For now, JWST's observations will serve as a crucial stepping stone, laying the groundwork for future exploration. As data from the telescope continues to be analyzed, scientists may discover unexpected phenomena on Triton that challenge existing theories and inspire new missions. The mysteries of this distant moon remain tantalizingly out of reach, but each new piece of information brings us closer to understanding one of the most intriguing and enigmatic objects in our solar system.